I always feel like we're on the downhill slope. So chapter 17, this is called Interpolating Polynomials. And this section kind of contrasts with what we did last time with linear regression. So with linear regression, we had a bunch of data points and we were trying to find a line that minimized the sum of the squared distances away from the line for the data. So today we do something totally different. We go like the exact opposite direction. We don't try to have any error in our data. We want zero error. We're not trying to minimize it. We're trying to pass through every single data point that we have. Okay, so this is in contrast to what we did last time. So today, if we have some data points, we're going to hopefully have fewer data points. That way we have fewer points that we need to pass through. So today, I'm going to have data points like this. And I'm going to try to find a polynomial that passes through those 3 points. So a polynomial that passes through these 3 points would be this parabola, probably. So a quadratic will pass through 3 data points. Guaranteed. So 2 points determine a straight line, 3 points determine a quadratic, 4 points will determine a cubic, etc. Okay. So in general, for n data points, there is a unique polynomial of degree n-1 which passes through those data points. We call this polynomial the interpolating polynomial for the data. We call this polynomial an interpolating polynomial. For the data. So if you have 3 data points, you can find a unique quadratic which will pass through those 3 data points. Okay, and there are tons of different ways to do this. We're going to talk about 3 today. We're going to talk about the brute force method. We're going to talk about the Newton interpolating method and then the Lagrange interpolating method. Okay, so we have 3 methods of finding these polynomials that pass through a certain number of data points. Okay, so if it's a straight line, I mean, everybody knows how to create the line between 2 data points. Okay, how do we get a polynomial like a quadratic or a cubic? Well, we're going to talk about that. So what would we do once we have this polynomial? We would use it to interpolate. Just like we were going to do for linear regression, we were going to say, okay, the line is basically going to approximate all the data around the line. Well, now our polynomial passes exactly through all of our data points. We're going to say, okay, that polynomial is approximating all of our data points. So we can say, okay, any other x value that I want to know, I can just plug it into that polynomial and say, okay, at this x value, my function value should be on this polynomial. So it's an interpolating polynomial. We're going to use it for any x value between the endpoints of our data to interpolate our data or get the y value for that corresponding x value. We're going to say it's probably on this interpolating polynomial. Does that make sense? Do you see how it kind of contrasts with linear regression though? Linear regression, the line may not pass through any of the data points, but you're using it to approximate the data. Well, it's similar for an interpolating polynomial, except interpolating polynomial passes through every data point. Okay. In both cases, though, you're using it to approximate what your data does. That make sense? All right, cool. So the brute force method for finding a polynomial. So number one, call this the brute force method. For finding a polynomial passing through n data points. So I'm going to say, for example, find the quadratic passing through got 3 points here, say 1, 0, 0, 1, and 2, 2. So find the unique quadratic passing through these 3 data points. So this is going to be the brute force way to find this quadratic function that passes through these 3 data points. Well, we know that the polynomial, we'll call it p of x, should be ax squared plus bx plus c. Right, that's the general form of a quadratic function. And if you had 4 points, you would say ax cubed plus bx squared plus cx plus d. You basically just create a general cubic polynomial if you had 4 points and do the same approach. So I have my polynomial and I want the polynomial to pass through these data points. So what I do is I say, okay, this is the x value. The corresponding y value should be 0. So p of 1 should equal 0. So that's a plus b plus c should be equal to 0. So I get one equation from my first point. Now you see where this is going. I get one equation for each point. So then I have a system of 3 equations, 3 unknowns. I can solve using a linear system solver. Okay. So p of 0 should be equal to 1. So p of 0 would be c equals 1. And then p of 2 equals 4a plus 2b plus c equals 2. So now I've got 3 equations, 3 unknowns. I solve my system, my linear system of equations. Thankfully, I plugged in x equals 0, right? Thankfully, that was a data point, something on the y-axis. That helps me kind of eliminate a variable automatically. So I got 3 equations, but really c equals 1, so I have 2 equations after that. So from here, I can get a plus b equals -1, and 4a plus 2b equals +1. Okay, does that make sense? So I'm not really using a specific technique to solve this. I could use inverse matrix if I were in Matlab. I could use Gauss pivot. I could use whatever. But I'm just using like an elimination or a substitution technique here. Okay. All right, so what do I do here? Probably I could substitute the first equation into the second equation, or I could do maybe elimination. I think I'll do -2 times the first equation. So I'll do -2 times the first equation, added it to the second equation, see what I get. So that gives me 2a equals, let's see, that'd be 2 plus 1 is 3. So a equals 3/2. A equals 3 over 2. So what will that tell me b is going to be? B is going to equal -5/2. Is that right? So my polynomial p of x that passes through these three data points is going to be 3/2 x squared minus 5/2 x plus 1. So that's the polynomial that passes through these three data points. So that's the brute, we call it the brute force way to get the polynomial. Does that make sense? If you had a cubic, you would have 4 equations. If you had a quartic, you'd have 5 equations, 5 unknowns, etc. So you can see the general brute force method gets a really large system of linear equations. So that's pretty computationally expensive, to be honest, to compute a high degree polynomial. That's computationally expensive. What's up?
So like on a test, this wouldn't be good to use over 3 equations?
Yeah, 3 equations is kind of the max. I've actually never asked this question on an exam, like use a brute force method, but I've been thinking about it today as we've been talking about it. I've been thinking, you know, if I made the numbers work out decently, it wouldn't be too bad to solve. So yeah, we'll see. We'll see. 3 is kind of the max. I might do 3 so you wouldn't be able to just create the line. 2 points is kind of silly. Like a straight line between 2 points seems kind of silly. Cool. Does that make sense? Okay. That's the first way. It's called the brute force method. So in general, for n points, to get n-1 degree polynomial, we need to solve n by n system of equations, of linear equations. So that's pretty computationally inefficient. So this is computationally inefficient. Solving big systems of equations is computationally inefficient. Even for a smaller system like 5x5, 6x6, there's a much faster, there are 2 faster ways, at least, 2 faster ways to get the polynomials, okay? So the second way is called Newton Interpolating Polynomials. So the second way to get this polynomial would be to use the Newton Interpolating Polynomials. So Newton Interpolating Polynomials. So if you use the Newton Interpolating Polynomials, there's a very algorithmic way to calculate the coefficients for your terms, your constant, your linear term, and your quadratic term. So the Newton Interpolating Polynomials have a very special form. So Newton Interpolating Polynomials say, okay, if n equals 1, P1 of x is equal to B1. Or should I call it B0? Yeah, B0. Yeah, we'll call it B0. If n equals 2, your polynomial should have this form. It should be B0 plus B1 x minus x1. So here, if you have 2 points, let's say, here's your points xi, f of xi, it's x1, f of x1. Here you'd have 2 points, x1, x2, f of x1, f of x2. So if you write your polynomial in this form, your coefficient b0 will actually be the same as the b0 you got for your first polynomial, p1, which would just be a straight line. Right, the 0th order. Actually, I think we should call this the 0th order polynomial, p0. Call this the first order polynomial since it's a linear function. So we call this the 0th order approximation. Zeroth order approximation. This is called the linear approximation. Linear or first order approximation. If you have 3 points, so you have another point here, x3, f of x3, you could get a quadratic polynomial. We'll call it p2 of x. It would have the form b0 plus b1 x minus x1 plus b2 x minus x1 x minus x2. So it's a very kind of recursive definition of the polynomials. It uses the previous polynomial plus a new term. So that's pretty cool. All you have to do is calculate this new coefficient b2 and add it to your previous polynomial. And if you had another point, maybe you have 4 points to work with, you would get that third order polynomial, p3 of x, we'll call it, equals b0 plus b1 x minus x1 plus b2 x minus x1 x minus x2 plus b3 x minus x1 x minus x2 x minus x3. I don't like it, but if I don't do it, it will be a little strange. I'll just leave it. It won't matter too much. So that's if we had a 4th point to work with, x4, f of x4. That would give us the cubic polynomial passing through those 4 data points. It would be the same polynomial if I used the brute force method to get it. It's just using a different method to get the polynomial. It's writing it in a very specific way. Okay, does that make sense? I'm writing it in a very specific way. Now, what are the b0, b1, b2, b3? Okay, what are b0, b1, b2, b3? So that's a question we need to answer now. So let's focus on p1 of x and p2 of x. So p1 of x needs to pass through 2 data points. So p1 of x1 needs to be f of x1. So that would be b0 plus b1 x1 minus x1. So that tells me that b0 should just be my first function value, f of x1. So B0 is just the first function value you have in this list of points that you've ordered somehow. We'll talk about how to order these points when we get to some examples. But for now, we just have a list of data points ordered. And B0 is going to be the first function value I have in that list of data points. Okay, does that make sense? And then also this line, P1 of x2 should be equal to f of x2. So that's going to be f of x1 plus b1, x1 or x2 minus x1. So that would tell me that b1 would be equal to f of x2 minus f of x1 over x2 minus x1. So your first polynomial, your linear interpolating polynomial, is going to be f of x1 plus f of x2 minus f of x1 over x2 minus x1, x minus x1. No shocker there, right? I just have an intercept and a slope. So that's your first order interpolating polynomial. I could mention that the P0 of x then would just be f of x1. So that would be your zeroth order interpolating polynomial. Zeroth order. Newton interpolating polynomial. And this now is our first order Newton interpolating polynomial. Does that make sense? So I found the coefficients B0 and B1. Well, if I want to get the quadratic polynomial, all I got to do is figure out what B2 is, because I already got B0 and B1. So P2 of x be equal to B0 plus B1, x minus x1, plus B2, x minus x1, x minus x2. So all I have to do now is make this thing pass through x3, comma f of x3. So P2 of x3 equals f of x3 equals f of x1 plus f of x2 minus f of x1 over x2 minus x1 times x minus x1 plus B2 x minus, let's see, x3 minus x1, x3 minus x1, x3 minus x2. So after some algebra, we'll get B2 equals f of x3 minus f of x2 over x3 minus x2 minus f of x2 minus f of x1 over x2 minus x1 all over x3 minus x1. So it's like a difference quotient of your two difference quotients of the 3 points that you started with. Does that make sense? It's a difference quotient of difference quotients to get B2. Questions? This is what we call a divided difference. This is one of Newton's divided differences. So this is called a Newton divided difference. It takes the previous divided differences and takes its divided difference, or takes their divided difference. So it's a difference quotient of difference quotients. So I'm going to draw like a little picture that helps you remember how to do, in general, all these divided differences. Okay, so if you were to get B4, you would take a new divided difference minus this divided difference divided by x4 minus x1. Okay. So let's look at a graphic or a picture that I like to use to remember how to get all these divided differences. So a table for calculating Newton's divided differences. All right, so the table I like to use, I start out with x1, f of x1, x2, f of x2, x3, f of x3, x4, f of x4, x5, f of x5. Let's say I have 5 points. That would give me a fourth order polynomial, a quartic polynomial. So B0 is right here. I've already got B0. It's the first function value, B0. Then I use these two to calculate B1, which is going to be f of x2 minus f of x1 over x2 minus x1. And that gives me B1. Well, if I wanted to keep going, then I would calculate these two, take their divided difference, call it f of x3 minus f of x2 over x3 minus x2. And then I would use those two divided differences or difference quotients to get the next difference quotient, or we call it divided difference. So in this case, it would be f of x3 minus f of x2 over x3 minus x2 minus f of x2 minus f of x1 over x2 minus x1 over x3 minus x1. And that's our B2. Does that make sense? So now, what if you wanted to get B3? If you wanted to get B3, you'd have to go all the way back to the beginning here and get this difference quotient, f of x4 minus f of x3 over x4 minus x3. Calculate the next divided difference, f of x4 minus f of x3 over x4 minus x3 minus f of x3 minus f of x2 over x3 minus x2 over x4 minus x2, and then use that and B2 to get B4. or sorry, B3. Does that kind of make sense? So basically this one would be B2 minus, we'll call it B2 star. So B2 minus B2 star over X4 minus X1. That would be B3. And if you had to get B4, you'd have to go all the way back to the beginning, go down to the last set of points, calculate the difference quotient, move to the next column, calculate the difference quotient, etc. So this is the graphic that I always picture when I'm trying to calculate these coefficients. I mean, of course, these end up just being numbers in a, I guess you could say, a matrix. And you just have to go back to the previous column, take the difference quotient of those terms in that column that are next to each other. So notice how the denominator for this last one kind of like walks back down to X4. And it walks straight back to X1. So that's how I know what the bottom denominator is going to be if I follow it backwards to where it started. That's how I get that denominator in the bottom. Kind of like this one, X4, X2. If I walk it back, it goes back to X2 and X4. Okay. So that's how I can calculate these things. We're not going to program this one. This is the first thing we've come up against that's going to be a little too challenging to just code on the fly here in class. So I'm not going to program this one in class. Okay, example. Example, find the second order Newton Interpolating Polynomial. Find the second Newton Interpolating Polynomial passing through the points 1, 0, 0, 1, 2, 2, and use it to approximate f of 1.5. All right, that's an x value. Oh, that's an x value between 0 and 2. So the solution, again, is very algorithmic. What I'm going to do is order my points closest to furthest away from 1.5. Actually, let me do 1.6. That way, there's no choice that needs to be made. I'm going to do f of 1.6. So the first thing we're going to do is order the data. Order the data. Closest to furthest from x equals 1.6. So that's how we order our data. We put the point that's closest in x value as the first point. We put the point that's next closest as the second point, okay? So our f of x table, x, f of x, what point is closest in x value to 1.6? Well, that's the point 2, 2, right? 2, 2. X equals 2, y equals 2. That's the closest data point as far as x value is concerned. What's the next closest data point? Yeah, 1, 0, 1, 0. And then the next closest data point, 0, 1. That makes sense? So now I've already got B0 right here. Got B0. And then what do? I use difference quotient to calculate B1. So this is going to be 0 minus 2 over 1 minus 2. So that's negative 2 over negative 1, which is negative 2. Or sorry, positive 2. And that's B1. Well, now I use the difference quotient here. 1 minus 0 over 0 minus 1 is negative 1. And then use the difference quotient between those two to calculate B2. So that's going to be negative 1 minus 2 over 0 minus 2. So that's negative 3 over negative 2, which is 3/2. So this is my B2. So my second order Newton interpolating polynomial, P of x, P2 of x, is going to be 2 plus 2 times x minus 2 plus 3/2 times x minus 2 times x minus 1. And that's how I'd write that interpolating polynomial if it were written in a Newton interpolating format. It's the same polynomial we found back in the brute force method. It just has a different form. We're writing it in a different way. It's a more clever way, I guess. It's the same polynomial. If you were actually to take this thing, multiply out all the factors and collect like terms for x squared, x, and constants, you'll get the exact same coefficients we got back in the brute force method. It's the exact same polynomial. Does that make sense? Cool. If I wanted to create the linear polynomial, I basically just leave off the 3/2 part. I would just have 2 plus 2 times x minus 2. I would just use those first two data points to create the linear polynomial, or the first order approximation. If I want the 0th order approximation, I would just say P0 equals 2. That'd be my 0th order approximation. I would just use the very first data point. Of course, I have to order the data before I do any of that. And I order it in terms of how close it is in x value to the point that you want to interpolate. All right, cool. Questions? Any questions? Any questions online? Got a lot of people online. Okay. I mean, when you have like numbers, it's not too bad to look at, right? It was pretty rough when I had that general table, had like a lot of stuff, but really, I mean, just once it turns into numbers, you just go back and do a difference quotient, you know, of numbers. And it doesn't look too bad when you just have numbers to work with. So doing a 5th order polynomial with numbers is really not too bad once you work your way through the chart or work your way through the table. So everybody agree? Questions? All good? All right, we've got two methods so far to get the polynomial passing through our data points. One more method called Lagrange Interpolating Polynomials gives us a different way to obtain the same polynomial. So number 3, Lagrange Interpolating Polynomials. So the last one, Lagrange Interpolating Polynomials. And it's going to assume that your polynomials have a different form. So your Lagrange interpolating polynomials are going to have the form. Let me write down the linear polynomial P1 of x is going to equal f of x1 times L1 of x plus f of x2 times L2 of x, where L1 and L2 are linear functions. So well, let's think about it actually. Where L1 of x1 should equal 1 and L1 of x2 should equal 0. And L2 of x1 should equal 0. And L2 of x2 should equal 1. Right, if I can make that happen, then I will pass through my two data points, right? If I can make this happen, then I will pass through my two data points. My P0 of x is just f of x1. So my 0th order polynomial is the same. I mean, that's a given. It's just the y value of your first data point, regardless of which method you use. It's pretty easy to calculate, regardless. Now, in the Lagrange format, we have our function value times a new function, L1 of x. L1 should be 1 if I plug in x1, and it should be 0 if I plug in x2. Okay? So L1 of x has this form. L1 of x is this linear function, x minus x2 over x1 minus x2. Notice that this function indeed is equal to 1 if I plug in x equals x1 and 0 if I plug in x equals x2. So this function does satisfy what I wanted it to satisfy when I plug in my two data points. Does that make sense? And then L2 of x will be equal to x minus x1 over x2 minus x1. And again, it satisfies what I wanted it to satisfy. It's 1 if x equals x2, and it's 0 if x equals x1. So then my Lagrange interpolating polynomial is actually f of x1 times x minus x1 over, x minus x2 over x1 minus x2 plus f of x2 times x minus x1 over x2 minus x1. So that's your first order Lagrange interpolating polynomial. Again, it's the same straight line you would get no matter which method you use. It's just writing it in a very specific format. Okay. It uses these Lagrange functions L1 and L2. So it's taking a linear combination of these Lagrange, what you call Lagrange basis functions. that are 0 at the grid points and 1 at the grid point where you want the function value to be 1, or 1 times the function value. Okay, does that make sense? So this is your 0th order Lagrange. Here's your 1st order Lagrange. Let's look at the 2nd order Lagrange. P2 of x. Well, that's going to be f of x1, L1 of x, plus f of x2, L2 of x, plus f of x3, L3 of x. So now we want L1 of x to be equal to 1. Or sorry, L1 of x1 to equal 1, L1 of x2 to equal 0, and L1 of x3 to equal 0. So basically I want it to be 1 when my subscript on x matches the subscript on the L. I want L2 of x1 to equal 0, L2 of x2 to equal 1, and L2 of x3 to equal 0, and L3 of x1 equals 0, L3 of x2 to be 0, and L3 of x3 to equal 1. So I want my 3 new functions, L1, L2, L3, to satisfy these conditions. Now, unlike Newton, Lagrange is not recursive. Like I can't use L1, L2 from the previous polynomial. I actually have to multiply them by some new terms. So now L1 of x is equal to x minus x2, x minus x3. So basically have to multiply by an extra term over x. I'm going to change the subscript color to match right there. So x1 minus x2, x1 minus x3. So basically in the denominator, you take x sub whatever L's subscript is minus the other data points. So L2 of x is equal to x minus x1, x minus x2, or sorry, 3 over x2 minus x1, x2 minus x3. So basically you take your x value where you want it to be 1 and subtract the other data points from that. And the numerator, you just do x minus the other data points. Okay. And so you should be able to tell me what L3 is going to be. Go ahead and write it down. See if you can go ahead and tell me what L3 is going to be. Right. So that's basically what you would plug into your P2 of x. Okay. In general, for n data points, L sub I of x is going to be the product of j equals 1 to n, but j not equal to I of x minus xj over xi minus xj. So the product is very similar to summation. You just multiply the next term times what you already have. Instead of adding the next term to what you already have, you would multiply the next term times what you already have. Does that make sense? So this is the way that you would write your Lagrange basis functions, L sub I of x, if you had n data points. So you do x minus x1, x minus x2, x minus x3 in the numerator. In the denominator, you do xi minus x1, xi minus x2, xi minus x3, dot, dot, dot. The only one you don't do is xi minus xi. Of course, that would produce 0 in the bottom, and that's a problem. And the one you don't do in the top is x minus xi. Okay. That makes sense? So you should be able to do any arbitrary size Lagrange polynomial at this point. So then your p sub n of x would be the summation I equals 1 to n of f of xi times L of x. Like that. Or L sub I of x. That's actually, if it's n data points, it's an n minus 1 degree polynomial. So I should actually say the polynomial is p n minus 1. So the n minus first degree polynomial is a summation I equals 1 to n of your function values times your Lagrange functions. And in Matlab, x is going to be a number that we want to interpolate. Okay, so to go ahead and plug that in our Matlab code when we get there. So first thing we're going to do is calculate the L's evaluated at that x value, and then multiply those by the corresponding function values and add them all together. Okay, does that make sense? So I could vectorize it, or I could do a loop for the summation part. So I could do a vectorization, then take the sum of that vector, or I could actually do a loop to do it. Let's do it as a vectorization. I've never done it that way. The product I'm going to have to do in a loop to get the L's at that x value, but then I can do the second part as a vectorization and take the sum of the vector. All right, so let's see. Maybe I should do an example. Let's do our example first, and then program this Lagrange int. So example, find the second order Lagrange polynomial passing through (1, 0, 0, 1, 2, 2), and use it to approximate f of 1.6. We didn't even plug it in, did we? Now I'm thinking about it, the last example, we didn't even plug in x equals 1.6. So if we go back up here, we say P2 of 1.6, what do we get? I didn't even do that. Don't do that on the exam. Don't forget to plug in your x value that you want to interpolate. So that'd be 2 plus 2 times negative 1.4 plus 3/2 times negative 1.4 times 0.6. So what do we get for that? .84. So that was the answer we were actually looking for in that last example. We should get the same number here, of course. We should get exactly the same number. But we're going to use a different technique to get that polynomial, to get that number. All right, so do the same thing we did last time. Order the points from closest to furthest away. So x, f of x. It's going to be 2, 2, 1, 0, 0, 1. So let's label them. This is x1, x2, x3. So our polynomial p2 of x is going to equal 2 times x minus 0, x minus 1 over 2 minus 0, 2 minus 1. I think I put them in the wrong order, but it doesn't matter because it's the same thing. But I should say x minus 1, x minus 0, 2 minus 1, 2 minus 0. Plus 0 times x minus 2, x minus 0 over 0 minus 1 minus 2, 1 minus 0, plus 1 times x minus 2, x minus 1 over 0 minus 2, 0 minus 1. So that's going to be 2 times x minus 1 times x over 1 times 2, which is 2, plus 0, plus, let's see, that's negative 2, that's negative 1. It's going to be x minus 2, x minus 1 over 2. So this is going to be x squared minus x plus 1/2 x squared minus 3x plus 2. So P2 of 1.6 I don't know, maybe it was better to leave it this way. 1.6 minus 1 times 1.6 plus 1/2 1.6 minus 2, 1.6 minus 1. Regardless, we should get 0.84. If anybody wants to double check, we should get 0.84 again. That make sense? Yeah. Cool. Cool. Questions? All good, all good, all good, all good. Cool, cool. Okay. Let's program it. Did we get 8.4 or 0.84? Sorry. Awesome. Let's program this one. And the thing that's going to help us program it is this formula right here, the general form. When we write it like that, that'll help us when we program it. So just keep that in mind here. Let's use that. So I'm going to create a new function file. Create a new function. I'm going to call this thing Lagrange int for Lagrange interpolating. You could just call it Lagrange if you want, it doesn't matter. We're going to output our y int. So that's our y value interpolated. And this uses the Lagrange Interpolating Polynomial of degree n-1 if n is the length of the data coming in via user input. So basically set it up the same as they had their Newt int set up. We'll have an x vector of data points, the corresponding y values for those data points, and then an x value where we want to interpolate. And then we'll go down here, we'll say n is going to be the length of x. And if length of y is not equal to n, put an error. Data vectors must have same length. So xx is the value where we want to evaluate the interpolating polynomial. All right, so first thing we need to do is probably calculate the L values. The L values. So we need to set up a loop to get all the L values. So L is going to be a vector of zeros. And I want to loop through each value in my L vector and get the L of xx, basically. I want to get L of xx. So for I equals 1 to n, this loop is going to calculate the L sub I of xx. Function value. And store it in the vector L of I. All right, so then I need to do for j equals 1 to n. If j is not equal to I, L of I is going to be L of I times xx minus x of j divided by x of I minus x of j. So there's actually a problem with what I've got so far. This line, 17, is fine. except for one thing. This is exactly what I have in my handwritten formula on the left. I'm recursively taking the product with the next term with what I already have stored in L of I. But L of I initially is 0. So if I multiply 0 by anything, I'll just get 0. So what I need to do is go back up here to line 12 and say that it's a vector of 1s instead of 0s. So let me go ahead and save this as Lagrange int. I'm not going to try it or anything yet. But basically what I'm doing in line 17 is I'm taking what's currently in L of I, multiplying it by xx minus x of j over xi minus xj for each j from 1 to n as long as j is not equal to I. Does that make sense? This is exactly the same thing as what's on the left over there. Handwritten formula. So this loop is doing exactly what that handwritten formula is doing. Questions? All good? All right. Once I have those L values, calculating y int is no problem. So now we put all of them together to get y int equals y of 1 times L of 1 plus y of 2 times L of 2 plus dot 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 y of n like that. Okay, does that make sense? Y int is going to be the function values y times the L values, the corresponding L values, just like we have in this summation, handwritten formula. So that is basically going to take our function values, which are the y values, times the corresponding L value at that x value that we've plugged in already. So I'm going to take the first function value, y1, multiply by the first L value, L of 1. Add them all together. So I can do this in a vectorized way. I can say y int is going to be the sum of y dot star L. All right, does that make sense? So I'm doing y dot star L to multiply the corresponding elements of y and L, and then I take the sum of that new vector to get all the elements added together. All right, y dot star L produces a new vector. The first element is y of 1 times L of 1. The second element is y of 2 times L of 2, etc. Okay, and then take the sum of that vector, which is a built-in MATLAB function. So of course, I'm cheating a little bit by using built-in MATLAB capabilities, but oh well. Typically, what you would do is probably loop through I equals 1 to n and say y int equals y int plus y of I star L of I, and start y int out at 0. So it'd be 0 plus y of 1 times L of 1, and then the next time through the loop, it'd be what you currently have in y int plus y of 2 times L of 2, etc. But this line 25 is much cleaner as far as MATLAB goes. That make sense? All right, I'll type the other one out in a comment. For I equals 1 to n, could say y int equals y int plus y of I star L of I. So this would be the classical way to compute the polynomial value. So we actually have to initialize y int to be 0. But we can use Matlab's vectorization or use Matlab Vectorization, which is way easier to, it's just one line. Well, for us, it's one line. That function sum has some code behind it that, we don't see, but it's probably just as efficient as our loop right there, 25 to 28, if not better somehow. Cool. Let's test it on the example we just had from class. Make sure we get 0.84. Okay, so we go to Matlab, create a script file. Let me make sure I save that. It's already saved. Okay. Let me create a script file. And this will test our Lagrange interpolation function. All right, so x is our vector of exit points. We said 2, then 1, then 0. And then our y values that correspond to those were 2, 0, 1. And let's say fx equals Lagrange int of xy 1.6. Run it. Hey, 0.84, look at that. Look at that, 0.84. So this is our fx Lagrange. Let's do the same thing with the Newton int function. We'll call it fx Newt int, or Newton Interpolating. And we use Newt int. Hey, both of them are 0.84. Both are 0.84. Cool. Questions? So what you need to do today for the Matlab grader problem is take the data that you're given, rearrange it, first of all, in your vector to go from closest to furthest away from the point. And then I think you're asked to give the 0th order approximation, the 1st order approximation, the 2nd order approximation, all the way up to like 4th or 5th order approximations. So basically what you're going to do for each time is plug in a different number of points to each function, Newt, int, and Lagrange. And those are already in the background of Matlab grader. You just have to call them kind of like we're doing here. I think in the Matlab grader problem, they're called Newt, int, and just Lagrange. So if you want a different order approximation, just plug in a different number of points. Of course, keep them closest to furthest away when you plug them in, but just plug in a different amount of points. Okay, cool. So I guess the one thing we didn't do was do the brute force method in MATLAB, but basically that's just setting up the system of equations that we got. So that'd be a little harder to program. How to program that for an arbitrary number of points? We could do it for 3 by 3, no problem. But for arbitrary number of points, I wonder how we'd program the brute force method. We'd have to be able to somehow calculate the nth power of the x values and create the system of equations kind of algorithmically, and then solve that system of equations. Of course, we'd call one of our methods to solve it, but setting up the system of equations, we'd have to somehow find a good way to do that algorithmically, make the computer set up the right system of equations. So I guess for each data point, you would create a row in your coefficient matrix. The first element would be the nth power. Actually, the n minus first power. The second element in that row would be the n minus second power, etc. And we can figure it out. I'm not going to do it though. Oh, does anybody want to take this class for honors credit? I have a project that you can do now. Basically create the brute force method function that takes an arbitrary number of data points, x and y, and uses it to interpolate x. If you want to set up an honors contract, that can be the project. Basically write that function file. Just think about it. I guess, I don't know, I think maybe you already have to turn in those honors contracts before the class gets too far in. I don't know, we've had some stuff kind of work out in the middle of the course before, so that'll be the honors project if anybody wants to do this class for honors credit. So, cool. Let me take the roll. Let's see, Brady. Matthew's here. Joel. Brett's here. Christian. Gabriel. Justin. Christopher Gardner, aka Swanbaum, right? That's Dr. Swanbaum.
He's actually.
Okay, well that makes him absent here. Okay. Chase Gatlin. Austin's here. Jacob Hill is here. Devin. Hopefully these people aren't in the chat. Okay. Ryan Reynolds. Welcome, Ryan. Jody's here. Wait, is Ryan Reynolds, is that Christopher? He's not pretending to be Ryan Reynolds? Okay. Oh, okay, okay. He has business to. Okay.
He's in here now. He wasn't before.
Okay. Haley. Haley was online. Gerald's here. Douglas. Matthew. Mathern.
Going? Yes, sir.
There's
For some reason I can't hear people. That's weird. Try again, Matthew.
Hey, can you hear me now?
It's so
Hello.
weird, I can't hear you.
What in the world?
Just type it in the chat. Ooh. That's fine, yeah. Brad.
He was in our coding class. So.
Dustin Miller? Got you, Matthew. Dustin, no, I don't know. Hagen is online, not in class. Matthew, there we go. Kevin Pham. I saw him online. Cord. Jasmine. Jackson. Navy. Mason. Dustin's online. Austin Toys. Let's see him. Presley is here. Steven's here. Andrew Webb. And Sam Witzel. Okay, sweet. Cool, cool. I guess we'll call it a day. Hang out if you have coding questions or are working on anything. We're happy to help.
Question about when you're going over Lagrange, are you able to multiplication sum?
Yeah.
Could you explain that? How we go from just this line to the line here?
Yeah, so if you plug in, let's say I equals 1. That's this one. I equals 1. Then in the numerator, you have j equals, well, not 1, but j equals 2. So basically start at 1 unless I is right. So j equals 2, you would say x minus x2 over x1 minus x2. That's these two. The product means multiply. J equals 3, x minus x3, x1 minus x3. So take these two, multiply by these two.
Wait, where'd you get this? Or is this?
Here, n equals 3.
Oh, okay. So we make this for then it goes to okay.
Yeah. So basically, like j equals 2 is this. Product means multiply. Multiply by the next one. You get this.
All right. Cool. Thank you.